if you want to promote your work, as you should, please reach out to Kelsey, and she will be promoting your work as widely as we can. Thanks for joining us. We're really happy to have you with us. All right, thank you. In the coming days, Henry, who is right there, will be giving the talk on Friday, how do imperatives motivate. There is no talk on Tuesday next week because it's election day, so we want to make sure that if you want to vote, you have this opportunity. And the last thing I wanted to remind you is that if you're interested in the conference that Arnold is organizing in April 6 and 7, the dead on science and values, revitalizing, I blame you, Arnold, for choosing that word, revitalizing science and values. The deadline is on November 15, and the details of the call for paper are on the website. Today, it's my great pleasure to introduce Vaidman, who is a professor at Tel Aviv University. He is now on leave in New York. Left work in the philosophy in quantum mechanics, foundational issues in quantum mechanics. Has done some important work on quantum teleportation, on the Elitzer Vaidman bomb tester, which I highly recommend that you have a look at what it is, because the name does not exactly tell you what that is, and on weak values. His work, I've read, I'm far from being an expert on the Elitzer Vaidman bomb tester, supports the many-world interpretation of quantum mechanics that David has also been defending. We're really honored to have you here today with us. Thank you, and the floor is yours.
Thank you very much for introduction. I'm very pleased to be first time in Pittsburgh. I knew all the time that this is the center of philosophy of science, and I think there are rare cases where a person worked during his career on foundations, and I'm one of them. And moreover, working on foundations of quantum mechanics, I think philosophy is very important. So this is, I think, it's at least better later than never. So I'm very pleased to be here. Go to my homepage. I have rejected papers, and they are the most important papers usually. So in the end, usually most of them are published somewhere, but this one, it's rejected many times. It's not published, so I think it's maybe the most important. Although I'm not so sure, but still, it's really philosophy papers, and I still learn how to talk to philosophers and what bothers them and how to explain my ideas to them. And in this talk, I don't know how much help you'll get from me as a philosopher. I hope you'll get something. But at least the beginning of the talk, it will be about teleportation as a physicist. So I will tell you what is teleportation, because I also was involved in this thing. Maybe small reminder. It's a little difficult for me to be in US, but I know that I was an officer in the army. My son now it's in army, but there is no point for me to go there. No one will give me an M16 to defend my country. But terrible things happened there now more than 20 days ago. I'm thinking about it all the time, so I cannot not mention. Okay, let's information transfer and teleportation. As I said, first I will talk about what's teleportation from physics point of view. But moreover, I will talk about experiments. So I was not involved in teleportation experiment. People who I know were involved. I was writing about them. And then it's more about this philosophical issue. I'm trying to say how the information goes from one place to another. And I think the main problem is that different people understand very different things about what information is. And in particular, we talk about teleportation. Teleportation is about quantum things. So we talk about quantum information, qubits. What is a qubit? A qubit is kind of, so I will try to discuss and define at least what I mean by qubit information. And before going to this, the main issue, what's happening in teleportation, I will consider what's happening with information when I take a qubit and encode it in several other qubits, several other systems. So I think it's kind of it's easier because the process is simpler, and but there are some elements which are already there. So then I will discuss transfer of information in teleportation. I will end with even simpler examples in all this. The one which I think essentially the paper was triggered by the work of Deutsch and Hayden. Because for me, I think now it's pretty famous work, and some people say, why it's not famous enough? But for me, it seems I don't understand it. So this is one of the things. So I want to understand it better. I think I don't understand how they go. I present my understanding, and then maybe if there is any way to connect. Okay. When I kind of supposed to
Around one.
Yeah.
We have half an hour of Q&A.
Okay. So teleportation. Everyone think about Star Trek, and I think Zeilinger put this in American Journal of Physics, this kind of thing. But you see, but this is science fiction. And as a physicist, I know that this is science fiction because there are all kinds of basic laws. The mass cannot jump from one place to another. So this is impossible. Now, in quantum mechanics, maybe it sounds even more impossible. Even you cannot clone a system. But I think it's not like this. Quantum mechanics allows teleportation. Why it allows teleportation? Because it says if you want to move an object like this here, it's made of electron, protons, and whatever. And it cannot that this disappear here and appear here. This is nonsense. But if there is an object matter here and similar matter here, if you only send kind of information, what is the object, then this is feasible. If you cannot move mass, but you can the shape. We use all kind of methods how to move fax or whatever. So this is feasible. And quantum mechanics says that really electrons here or electrons here are exactly the same electrons. So to move this object here, we do not have to move electrons. All what we have to move is just the shape, the quantum state. In fact, I believe everything is quantum. I believe I'm quantum. I believe just I'm a quantum wave. So to move me to the moon, all what you have to move is just my quantum state. Electrons in the moon are exactly the same. Not that I believe that ever we will be able to move teleport macroscopic object, but conceptually it's possible. So just we need a lot of mass on the moon, and then this mass on the moon will become me later. Of course, the part of this I will disappear in another place. Before it was like this, but later, no. So, so let's start with the simplest quantum thing, qubit. Two-state system, spin. I bring a spin particle, and I want to teleport it. All what I have to do, I perform some measurement on it. And I end up with a little information, 2 bits. These 2 bits I send by classical channel to other place. And there is some manipulation here, and the qubit is there. And this was done by Bennett and company, Asher Perez from Israel. And I think it was inspired by Wisner. And when I read the abstract, I was extremely upset. Because before I was working on non-local measurement, and reading abstract, I knew how to do this. Why I didn't touch this question? And still, my way to do it helped me a little. I generalized it continuous variables. So in continuous variables, you give me some quantum state of continuous variables. I do some manipulation. I get two numbers. I send these numbers by classical channel. I do some manipulation, and I reconstruct these numbers. And I reconstruct the state, the function. It was a continuous function on the left. Now there is the same continuous function on the right. Now, what's paradoxical, what's very strange about teleportation? What is really sent? Before there was some preparation, there is quantum channel, whatever, but this was before. After somebody brought me the spin, I only sent 2 bits to this other place. And this spin, I need a lot of information to describe it. It has this, in fact, 2 numbers, 2 real numbers, this P and phi. This is a way to write this quantum state. I need P and phi to describe it. And I send only 2 bits, and somehow it is here. And here I send 2 real numbers, and I get a function. The function, it's infinite number of real numbers. So this is really paradox. Now it's not so complete paradox. It's not that I send 2 bits and get get 2 numbers that I can read. I cannot read. I get it in a quantum way. I have here a spin. To describe it, I need P and phi, but I cannot read these 2 numbers out of spin. And the same here, I cannot read all this function. It's not written, but it is there because only for this function, the probability to find this will be 1, like here. And the same here, I need this P phi is necessary for this measurement because there is probability 1 to find it, kind of truth value. There is some experiment which I know that will succeed with certainty. And this experiment characterized by 2 numbers. So I think 2 numbers are there in pretty strong sense. Not in the sense that I can read them, but still there and the same about this rate function. Okay. Now I said that I will talk about experiment. The first paper was sent with experimental teleportation with the idea of my friend Sandro Popescu, done by Di Martini and in his group. I think it's not teleportation. It's a remote preparation. In this experiment, they have to get teleportation we need a channel, entangled pair. According to this experiment, you take one of this pair and you put on this pair your quantum state. They write in the pair preparing the unknown state. I think as philosophers, you say, this is nonsense. There is no way to prepare a known state. This is just contradiction in terms. So this is really not teleportation. More or less at the same time, a couple of months later, Zeilinger, with Dick Bauminster and also my friend Harald Watzwerker, sent this paper about teleportation, which is conceptually much better. They really have in the experiment they have a channel and they have particle in which I bring a quantum state. I said in teleportation I bring you a quantum state and you move it to another place. Di Martini didn't do this. He brings you to his lab, asks you to prepare a quantum state on his device, and this quantum state will appear somewhere. In case of Zeilinger experiment, this was better because the real quantum state brought photon. this polarization was brought in one place, and it appeared in another place. But this experiment still, I would not call it teleportation, because it's not that he could send it, said that we had some clicks, and now say, oh, now the state is there. What they succeed to do, they put some detectors there, and if they find it, if they find the photon, this photon will be in the right state. But they don't know that they'll find the photon. Maybe it's a vacuum, or maybe it's 3 photons, or maybe something else. So I and not just me talk to Zeilinger all the time that you have to correct it. This was corrected sometimes later, and no one kind of pay attention on this correction. This is really real teleportation. You change some parameters in the original experiment, and then really you put particles here, you get some clicks, and you know that there is particles there. At least if your device is ideal. There are all kinds of imperfections, but the question, if your device is ideal, will it do the job? So this does the job. Maybe it didn't got so much attention because there was another. They admit this. They admit that in our previous experiment, the teleported qubit had to be detected. They admit that the previous experiment here is not great. Maybe it was not too much attention because other people, Sam Brownstein, who found a way. When I found this continuous teleportation, I thought it's completely theoretical idea. I didn't realize that using squeezed light you can do this very easy. And so Brownstein makes this experiment of my type of continuous variables, and it doesn't have this problem, other problems. So so these are the experiments. I have to mention something else about Brownstein. He and I will not talk about continuous teleportation. This is simpler. So let's come back here. I bring a spin, perform some measurement, get some outcomes, 0, 1 in 2 channel, and send it with 0 and 1 in 2 channel to other place. And Brownstein published a paper, Quantum Teleportation Without Irreversible Detection. Essentially, it's the same story. The only difference, we keep coherence. We just, like we do this, and, oh, sorry, I want yes. We do this, but when, after this measurement, we don't look on it. Usually we perform this measurement that we end up with 0 and 1 in 2 places, but this was inside closed box. There is this 0 and 1 in closed box, but it was not measured. So it was still quantum. So really what happened, they didn't send 2 bits. They sent, this was 2 bits, but in fact this was 2 entangled qubits. When you don't look, if you have a system with 2 levels and you don't know what's inside, this is really a qubit. So what teleportation does? You start with a qubit here and it's there. If during the process you send 2 qubits, there's no paradox. I would say it's no teleportation, definitely nothing paradoxical about this story. Let's come back to the original teleportation paper. We prepare EPR pair, spin, 2 entangled spin. We bring our spin. We perform what's called Bell measurement, which gets 2 possible outcomes. There is two of them with 2 possible 2 bits altogether. And we send only this classical information here. Classical information. This picture of their picture I borrowed from them, and then we can make some modification of this particle, and this has become this spin. In fact, I don't know how many of you saw the mathematics of this. Okay, so I think it will be very useful. It's extremely simple mathematics. There is almost nothing there. You say, this is an EPR pair with This is an EPR pair, and this is our qubit here. So this is a quantum state, the original quantum state. All what was done is just to realize that you can take this quantum state and rewrite it in a different form. The same quantum state, you can write in different bases. So now this was written in the original one. It was a product of particle 1 and this entangled state of 2 and 3. But now you can take particle 1, the system which you bring, and the one of the pair, and make decomposition in what is called Bell basis. This is 4 orthogonal states with which spans the whole two spin particle. You can make a decomposition in Bell basis, and what will happen on the right side, corresponding to each one of them, will be essentially the same, the qubit which we want to teleport. In one case, it's just the qubit itself. In this part, you see, you still have P and phi. The qubit is P and phi. The same, there is P and phi, but instead of plus here, there is minus. So what it means that you took a qubit and you rotated 180 degrees around the axis. And you have 2 more. All of them are just 180 rotation around different axes. So if you know which Bell state you are, you know what rotation to do to get this. If you rotate it, you can get the original qubit. So this is exactly the 2 bits you sent. You send which kind of rotation you have to do. And the whole physics and whole mathematics is just to write this state in this form. And then you get teleportation. There is another maybe issue which I also can spell out how you can do it conceptually easy, the Bell measurement. As I said, you have to measure these 2 systems in kind of non-local basis. It's local because they're now all together, 2 particle basis. How to perform Bell measurement. So for Bell measurement, you can take spin as a 2-level system and make a coupling to the first one and then second one, move it. And depending on what's happened, it might flip or not flip. And also do the same about the second one. These are these 2 bits which you send. And in fact, I'll also show how to perform this Bell measurement exactly. What you do is a rule. What is your rule? When it comes to your spin, if the spin is up, then you flip. You start with 0. We always start with 0. And if it's spin up, you flip. If you, in fact, it's continuous, so it has a second one. It may be up. If it's up, it flips. Every time up flips, and down not flips. Nothing whatever. This is a rule. Why is this rule? How does this rule make Bell measurement? You see, this is a Bell state, and this is a 4 Bell state. Consider the first one. We send a particle with this rule, and it passes through them, and there is superposition, 1 up, 1 down. So it will flip only 1 time. Maybe in this part it will flip the first time, and second time. It doesn't. We will not know where it flipped. We know if it flipped or not. So for this state, it will be flipped. Also for this state, it will be flipped. For this state, it will be flipped twice, which is not flipped, or not flipped, which is not flipped. So for this state, we'll get this one, and again here. But this is not enough. In the end, we can distinguish between pair and another pair of Bell state, but not all 4 Bell states. Another simple mathematics that if we write this Bell state not in a Z basis but X basis, spin X basis, then it will look like this. It's just identical. So the second one, when we'll run, will look not on Z, it will look on X. So the second one will look on X. And as you see, here it's also 1 up, 1 down, so it will be flipped. But here it will not be flipped because flipped twice, not flipped or not flipped. And again, not flipped. And again, and here, so now we have 4 different situations. This is Bell measurement. So now if you want to understand mathematics or physics, this is the whole story. The only story is that It's not necessarily as a real Bell measurement, not always done like this, because it's very difficult to make qubit interaction. But it's easier to make interference. But conceptually, this is how we can think. Okay. So now we'll come to more this philosophy, what's really moved, what's not. So we have to understand what defined all the concept. So my definition of a qubit, which is also qubit is a state. Qubit is a known quantum and unknown quantum state. It's important it's unknown. Of course, one can talk about known quantum, known qubit. But if you just moving a qubit, the meaning it's moving a known quantum state. And in teleportation papers, they really put this like this. Sometimes they put unknown qubit, but qubit for me it's unknown qubit. And so it's quantum state. Quantum state should be in some system. But I talk about spin. But there is no real difference if it's spin or this. There are two boxes and the particle can be here or here. If there are two states and it has the same state. Now in real life, very often we can put a qubit in at the two-level atom. And then we have the two excited ground. This is common use qubit. But so the first, if we have system with two levels with a known state, and the system doesn't matter, the state matters. But moreover, the system does not have to be just two levels. For example, if I have two spins, it has more degree, it has four possible orthogonal states if we talk about spin, but it might be a qubit. This, for example, is a qubit. It has this exact, we have two orthogonal states, up, and down, down. And even the system might have more states, I will still call that this is a qubit. Or even I'll have a continuous variable, and people send these qubits in continuous variable teleportation or any communication. Just I can say that particular this physics is psi of x. It can be everywhere, but I will call two states out of this infinite number of states as particular state, and call this as a qubit when I consider just the Hilbert space of this being here or being and being here. And but again, this is sometimes not so. So is a qubit a system? No, it's not a system, but we need a system, otherwise there is no qubit. Because the system doesn't matter. I can make a swap from one system to another of the quantum state. So there are these two numbers which I say they describe qubit. They definitely describe qubits, but they are not equivalent to a qubit. Qubit is something with a known quantum state, cannot be cloned. If I know P and phi, I can make many of them. It's P, phi, to these two real numbers are much, much more than qubit. Yeah, but this is, so qubit is a quantum state which has it, which I don't know. We need a system. Without system, there is no qubit. Now I also distinguish qubit and information about qubit. Sometimes it's the same, because if I have some quantum system, and so I will say the qubit is information. Sometimes people say the elementary unit of quantum information is qubit. But I don't say that there are situations when I don't have a qubit, because my definition of a qubit, I need this. I look on system, maybe big system, composite system. In this system, I need to see this kind of state. Sometimes I have a system which I don't have. I cannot. It's not there. It's mixed state. It's whatever. Still, this system allows me by some operation to create a qubit. Then I will say that this my system have information about qubit. And when I'm asking about information transfer, this is what I'm asking. I look on all this system, where this system move, because I believe without system, no information, no qubit. So where is it? If I ask where there is information, The information is where there are those systems out of which I can get my qubit. And again, the physical property of this system is not important. The only thing may be important for me where they are located, so I can ask where the information is. Because I believe that the information, I want to say that in teleportation, we move from one place to another. So I need to put, what does it mean, this information? I think it's information has location. Location of quantum information about the qubit, location of quantum system from which one can create the qubit. So this is kind of the definition. I think this is usually not spelled out, and maybe sometimes people understand different things, so they claim different things. This is my definition, and I don't think it seems to be natural. I don't know the only possible. This is definitely not, but it's all rely on this kit. Okay. So now I will consider. I consider encoding qubit and what's happened to information about this qubit when I encode it in a system of 4 qubits. This is 4 spins. I don't know. I'm considering just 1 qubit, but we have one spin, and then we have a system of 4 spins. And I want to put my qubit from the system of one spin to this 4 spin. And the interesting part here, Peter Shor, a part of making quantum computer, he also was the first to find error correction. And he had a 9 spin code. Then people improved it to a 5 qubit. This is a 4 qubit, which I cannot, which is essentially can make a kind of, it's not error correction code, it's error prevention code. I can, after encoding, if I can measure a particular space, and in this way I can keep my state from errors. And the wise thing to understand, when this is a way to encoding. So from this state will be encoded in this way. What's important in this way? It's kind of a symmetric. You see, there are 2 orthogonal states. This orthogonal to this because of 2 reasons. Here it's plus, and here it's my kind of bell states of here and here. Clearly, this is orthogonal to this, and then we have this coefficient as before. Here we have up and down on one system, and here we have this is kind of up, and this is kind of down. What's interesting about this, that if you take any of the particles and lose it, the information is still there. The information is not lost when you take any particle out of the system. It's still the full information of a qubit is still there. So let's see what's going with the information, how it works. So we start with this, and clearly we have a product. This is still in a kind of 0 state. 0 state is this state. This is a 0 state of this 4 spin system. And clearly the information, there is nothing, no P, no phi here. P and phi sits only in particle, the original particle. The next stage, we make a swap. Make a unitary operation between this system and this. I don't explain now exactly how, although essentially I will explain it by the procedure. And so now this one will be 0. It will have no information, and all information will sit in these 4 particles, like this encoding. This is the encoding of this state. So this is swap, and clearly the information is here. And as I say, the interesting part, clearly information is here. Out of these 4 spins, we can get the qubit back. But it also, in any 3 particles, for example, 2, 3, 4 particles, we can also say it's also here. If we just eliminate particle 1, we have only 2, 3, and 4. We still have the same, we still have qubits there. Now I explain, I prove it. How I start with
just the 3 particles and get the spin back, my qubit back. If you look here, we can this is a 2 orthogonal state of 3 and 4. And here we go to particle 2, and if it's down, we flip the sign. We have conditional flip of a sign of particle phase, essentially, of particle 2, depending on the state of 3 and 4. So condition on state of 2 and 3 on 4. So in one case here, when this is minus, we will make a flip, minus and down. And here it's plus, so we don't do anything. And of course, we don't do anything for up in both cases. Only if this one will have flip. When we'll have flip, if this is plus, then this is exactly like this one, so we can take it out. So we'll get our qubit now on 2 particles. This orthogonal to this, our qubit move to particles 3 and 4. Particles 3 and 4, we can make a swap now between 3 and 4 and 1 back to get it back. Everything is reversible here. There is no, everything is unitary. So essentially, I can encode this spin in these 4 spins by interacting only with 3, 4, and 2, not interacting with 1. Which is also kind of original, kind of strange thing. But the main thing which I want, why I had this example. Look at this stage, and look only on particle 2, 3, and 4. They have information of a qubit, but if you look on the state of particle 2, 3, and 4, it's really a mixture. You cannot find that you cannot find in any degree of freedom that it's just a qubit of some orthogonal states. So not every, sometimes we can have orthogonal information about qubit without having a qubit. To have a qubit, we need this states. Square root of p up plus e to the I phi 1 minus square root of p down. Nothing like this can be look on this, but information about the spin is there. Okay. Spin do not carry qubit, but have information about it. So this is the procedure, the teleportation procedure. So let's go to the main thing. In teleportation procedure, we have an EPR pair. One far away and one is here. Here we bring our qubit and we perform our interaction. First, this local interaction with this quantum kind of system. This is the situation before we did anything. So we are ready. We have a measuring device. Again, I split this measuring device of Bell measurement to 2 parts. First, I have a quantum coupling with some quantum small particles, and then I look on my quantum particle. Because as Brownstein said, we don't have to look. We just can send them, it still will work. But it will not be teleportation. We need to send classical teleportation. Classical is outcome of macroscopic measurement. So we need this measuring device, which will look on this. But of course, before we start doing anything, the state is just here, and it's not in this other place. And I write this quantum state. I believe everything is quantum. Of course, we have particle 1 and 2 of EPR pair. We have this is our measuring device quantum part, and this is our measuring device classical kind of part, the big part. It's ready, and this one's 0, and they're still 0. So on the next stage, we move one of them. When we move one of them, now all this clearly, this is unitary evolution, so everything is still there, reversible. But it's not here anymore, it's became entangled. Although it's only kind of, we don't move, it's conditional. We move these things conditional of state of this, but the state of this became entangled, so it loses its state. Maybe some language decoherent. But clearly, it's inside this, and then we make another one. So now it's inside this, and this is a quantum state after this procedure. So I didn't after these two elements, we didn't look this macroscopic device on our quantum state. We just make this coupling, which I discussed before about Bell measure. So we are here. The macroscopic is still ready, but this one knows they have 1, 1, Bell state 1, 0, another Bell state 0, 0, 0, 1. This is really kind of measuring of the Bell state. And it's all here. And and this state became this state. They're not equal because we made interaction. After the interaction, we get this. Now, this is nothing surprising. What's surprising is that if we look at this state, the information about qubit is now also here. Of course, it's here. We had coupling, so we spread the information between these systems. But now, if we look on this quantum system, we see that we can, looking just on this and particle 2, we can reconstruct our qubit. Because, we just look. If it's 1, 1, this is a qubit. If it's not, it's 1, 0, just make particular rotation. So this gives us what kind of transformation we have to do to get this, or maybe not to do anything. The qubit is already in this particle. It's interesting that the same, we don't have to look on this one. We can also look on our original thing, which is in one of the Bell states. The Bell states have the same information. There are 4 different Bell states, and each Bell state tells us what correction we should make. Okay. The next one, we perform the measurement of our microscopic system to make a measurement. And now this ready will become not ready, but it will read the outcome. So I'm an extremely strong many worder, so I believe what will happen, the quantum state is written like this. But this is macroscopic, different outcomes of reading of macroscopic device. Some people believe that if you perform macroscopic measurement, you split the word, or you also split the word. It's I agree too, but you maybe even collapse the word. So we have then from now on, I think we have to look differently on every branch or every part of it. In many words, it's all one state, but each one of them corresponds to different words, different outcomes of quantum measurement, macroscopic quantum measurement. This. So let's look on these different words. What's important in these different words, that information is here, but it's not here. In every one of these words, if we'll take this and this, the information is there. Again, here we can take, instead of this, maybe we can take this, these 2 particles. They have the same information like this one. Or take the measuring device, which also has 1, 1. We don't need this. We can just look on our classical device. It's all, but together with particle 2, we have the qubit. Without particle 2, we don't have the qubit. Let's put them together. You see, after Bell measurement, in every word, information about the qubit is located in remote particle 2 and various other things. But without particle 2, we don't have it. Now, information, I believe we can talk only for observers, because observers send information from one to another. This is the meaning. So from one, I think it's really crucial that after this Bell measurement, we really spread information. Before, the information was clearly here. This particle may be in another galaxy. So Bell measurement moves the information from one place. It doesn't move it to another galaxy. If I look here, I don't have it. But now, if I'm here, I also don't have it. Now it's spread out far away. Motion here spread out information in a non-local way. For every word, in every word. So we have something kind of superluminal if we talk about information. Again, why it's in superluminal? Information is a concept of an observer. Observer live in a world. Within the world, we can talk about something superluminal. It's still normal physics. In normal physics, there is nothing superluminal. If we talk about physical operators, whatever, nothing changed. But let's look again this time. It's we had something here. After this operation, it's here. After this operation, it's here. And after this operation, this is a Bell measurement. Yeah, it was just local interaction, but this is a Bell measurement. After this operation, it's here. So this is my superluminal story. And this story in every word. This is particular word. Now, single word universe picture, and the many word, one word picture in the history of this word. If I talk about collapse, this is exactly the story. If I talk about many words, I have to be careful because this is okay. Even in many words, this evolves in this way. But this evolution doesn't exist in many words. In many words, from here, you go to all of them. So we really cannot consider, I cannot consider evolution forward in time in many words. There's no meaning for this because every time I perform quantum experiments, several outcomes, I get three, I get all outcomes. How I still can think about how we, in fact, in practice, see that. We have memories, we have performed experiment, we can think about our history and try to think how our history evolved. So when we have records, in our records, we can think about our history, and there we say, oh, this kind of strange thing. Here it was with velocity of light, but this result happened after we perform measurement. In our history, we get some kind of superluminal property. The information moved from one place to two places which are far away. And this is from one of the referee reports. Why not just to use standard Everettian line? The branching propagates at speed of light, so there are no non-local changes. So I understand here the branching, or maybe this is what's happened with the branch. I don't know, but this sounds strange because for me the branch also needs this. This is part of the story. As till now, people didn't offend too much what I put in encyclopedia. The beginning, the main equation of many word interpretation is this one. The wave function of the universe is superposition of wave function of words. So every word is everywhere. What is the word in many words which spread with speed of light? This I'm trying to ask from David for a long time and still don't get an answer. And
not one you've been happy with. Yeah.
I don't understand. I don't understand the answer. And I want to mention some. If you look on all words together, there is no action at the distance. If you look on particle 2, nothing happened to it. The quantum state is the same mixture. Before Bell measurement, after Bell measurement, nothing happened. But still something's kind of interesting happening. After the Bell measurement, clearly the information is here, but also the information in here and here. That is, it looks like, although nothing changed here, but there is information about this also here. In all words together, even after Bell measurement, the information about the qubit is located in vicinity, like of course, but also in remote location. So maybe this kind of to make it to feel better, I think it's good to consider a simple example, also considered by Deutsch Hayden, more or less, which probably give flavor and maybe give some understanding about this feature. Consider just a spin, and I'll put some magnetic field and rotate it by angle theta. Clearly, there is a lot of information. There's magnets, there are all kinds of devices. So I have a lot of information. But now I ask, does spin knows about this? And spin knows because it was rotated by angle theta. I cannot read it really, but I know it's happened. My spin rotated by angle theta. The quantum state was only up, and now it's this. So this is local information if I do this operation. But now consider, so the angle from 0 go to theta. Consider now an EPR pair. And I do the same. Essentially, I had the same kind of macroscopic story. I bring magnetic field. Do it again. I bring magnetic field. During magnetic field, it's rotate. It's rotate everything. The physics doesn't change. But this is a quantum equation. It was this state and this every up rotated exactly in the same like this. This is up state go to this, and down state goes to this as a rotation because we have two states. This is particle one. It was rotated in this way. However, there is no local information because original EPR, this particle is unpolarized. It has the angle is completely uncertain. If you have completely uncertain and rotated by theta, it's still completely uncertain. There's no any change. No local change. No local change. Now, it doesn't mean that the information is not written in spin. It is written in spin because relative spin changed. Before, in standard EPR, up, down, there is angle pi between the spins of two particles, whenever you measure. Now, the angle is not, it's pi minus theta. This one is rotated. So there is a non-local information. Even we didn't touch this as a particle, but information, if you look on spins, now it's only here. The claim is locally, you cannot find it not here, you cannot find it here. Only in non-local way, or if you have some non-local reference, you also can find this information. It's one of the reasons why clearly you cannot find it locally, because essentially you can also this state equals this state. You can write it as rotate as the other spin is rotated. So it means that instead of putting some magnetic field here, you could put opposite magnetic field at the same time here. It will do exactly the same story. There's no difference. You will never be able to know if it was put here or it was put here. And this Deutsch Hayden somehow succeeds to say it because they have the whole program with descriptors and Heisenberg and whatever. But I think it's I don't think it's help us here because if I have this definition that information is something which I can take out and get my qubit back. They say locally inaccessible. And they say it about this information here. Why is this is exactly what moves. So some kind of things we can we come here, put information here, and now we move it with these 2 bits. But it's not locally inaccessible. It's inaccessible without particle 2. The main thing is here. If this will not be here, if I will just destroy it or send it to any other place, they cannot get the information. To get this information, they need particle 2. It's necessary. And if I look, these are not better than this one or than this one. These are exactly the same story. And so I cannot understand this concept. And again, the referee says on Deutsch Hayden view, there is no contradiction in claiming that one can have complete but locally inaccessible information about unknown state. Especially when he put complete. If it's complete, we don't need anything else. Maybe if it's locally, unlocally, bring it far away. But the whole, without this particle, no way, in every word, without every particle, without particle 2, the information is not there. So to say that it's somehow sitting here and fully, I cannot understand what it might mean. So I think this is a time for conclusion. As you said, well, in teleportation, immediately after the Bell measurement at every word, we need the remote particles to reconstruct the qubit. Apart from the particle, we need to know only in which word we are. So this is clearly the information is spread out non-locally because we need this as a particle in every word. I also say that mostly is there because what is here is just 2 bits, but clearly it's spread non-locally. In collapse theories, teleportation demonstrates action at a distance. Qubit splits immediately to remote location. Information we also see. There is also any kind of measurement in EPR from my point of view tell us similar thing, but this is slightly different ASCII. Many words avoid the action at a distance on the level of all words together. If we look on particle 2 in all words together, unpolarized electron remained unpolarized electron, nothing happened whatsoever. The word was split non-locally in different ways. So then when we'll tell with which word we are, we'll find our state. Local measurement split the word, which the words are non-local concept. So this is the way I see it. And but again, to discuss if I'm right or wrong, one has to be very careful. You agree or disagree, or to define what information is and what the word is. Thank you.
So as we always do, we'll take a 1 minute break in case